Welcome back. Hopefully you had a nice weekend. I wanted to take a look at the end of project 3 to talk about like the question prompt is like, where do you see the biggest difference, and what are ways you can quantify error? What are other calculations you can do? There's more than one way to do any of these questions, but it's usually that's the hard part for engineers. It's like you can do whatever you want, but you do have to do it with like a quantified, specific and measurable outcome, if that makes sense. So I wanted to spend time doing that. Last time it seemed like, let's see, so we had our like 118 to 125 centimeter chord. We guessed, our best guess was that time period was going to be 2.2 seconds, and we measured it. It was 2.15 plus or minus like 5/100ths of a second. So just with force and tension, we could get a lot of the motion correct, like at least like time period, frequency, probably even amplitude is pretty close. Changes a little bit, not a big deal. Right now I have a solution that is, this one looks like it's a 1 meter long pendulum. So let's change it to match same length that we had on Friday. So 1.18. Are there any differences in like the output? Like between linear and nonlinear, because that's really what we're comparing here, linear and nonlinear. Is there any difference? They look like they're overlapping, right? What if I wanted to see like the actual difference, like how much error there was between one and the other? How would I find like the error? We could look at percent error. Yeah, how would I do that? Okay, so which one's actual? The linear or the nonlinear? What do you think is like your most accurate? Linear? Different? Nonlinear? So let's take a look. We can take I'm just taking the plot from above, but I'm going to turn it into one plot. And so right now I'm not deciding like which one's more accurate. I'm just going to look at the difference. And this is a great way that you can figure out like, if it's always 0, then there is no difference. Like they're both giving us the same answer. But what we see here is that there is a growing difference. And part of that is not so much that linear or nonlinear is more accurate here. It's that numerical integration over time introduces a little bit of error. That's a whole nother kind of subject, but if you're trying to figure out like how close are these things, they're within 1/10 of a degree for both of those kind of swinging time periods. It's very easy way to kind of quantify, like, what is the error that we're seeing. Just take two values, subtract them. You can divide by some known solution if you want, get a relative, but it's easy enough, right? What was the way? When do these graphs get further apart? Like, when do we increase error? Yeah. Longer, so longer time will increase error. What about for the same amount of time? Because at one point we saw a blue curve and a red curve. They were different. Why were they different? Yeah. Different period. What led to a different period, though? Because it's the same, both of them are just considering tension and gravity. When we come back up and look at, like, what is our equation of motion? One of them, our equation of motion, is that acceleration is always g over L times theta. The other one is g over L times sine theta. So when do the answers start, like, diverge? When do we start getting two distinct answers rather than, like, just one curve?
When you have a larger starting input, because then sine theta can't be approximately the theta.
Yeah, so the bigger our initial angle, the more we're gonna swing, and so the bigger the angles get. It could be big initial angle or big initial speed. Both of them will, like, give us the same kind of error. But as this amplitude increases, we get big error. How small is small enough? 10 degrees feels like it's small enough, because it's the same answer. It's within, like, 0.1 degrees of the nonlinear. When is small enough for an angle? This one, there's no wrong answer. How small does it need to be? Is 10 good enough? 10 degrees? Seems fine, right? How about 15? 30? 100? 100 seems big, yeah. 90, anything bigger than 9. So maybe 90? Is 90 our cutoff? 90 degrees. Smaller? 80? What is it? 1? 1 would help. Yeah, 1's definitely small enough. Because 10 seems small enough. I mean, you can try different values. For me, rule of thumb is kind of like 30. That's my rule of thumb. If it's bigger than 30, I don't consider it a small angle anymore. Less than 30, yeah, it's pretty close. So let's do a test. Change initial angle to 30, and then we'll regenerate our curves. And sure enough, there's a difference. It's not the same. There is an error. The error is bigger. Now it's kind of like, by the end, I'm up to 4.5 degrees, but how about my time period? How close is time period? Yeah.
And the periods are still relatively the same.
Pretty close. Yeah, they're pretty close. Are they within 1 second of each other? Let's look at the x-axis, right? All right, so we're doing some we're saying, we're making a statement. Time period is the same. we can, and you can either say that or you could say time periods are different, but something. So we're making a statement that time periods are the same. Let's copy this, throw it over into here. And again, say whatever you want, but just back it up. So if I want to say time periods are the same, I can come in here and kind of draw a line between the two. Definitely within half a second, right? Because it's a 2-second time period and both time periods are pretty close to 2 second or whatever, 2.1, whatever. Oh yeah, we said 2.2. So they're both pretty close to 2.2. Is it 2.3? Like, is it a full 1/10 of a second different for this time period? I don't even think so. I think it's less than. So I could say t linear equals t nonlinear plus or minus 0.1 seconds. So they're within a 1/10 of a second from each other. Even just looking at this, even just looking at a plot and saying, like, here's where I got that information. I could do a Fourier transform, find the actual like frequency that it's oscillating, but we're just trying to interpret some results that we're getting. Are the amplitudes all the same? How about amplitudes? Because those were the two main things that we kind of looked at on Friday. It was like, we can look at time period is frequency is directly related to natural frequency. How about amplitude? That was the other part. Is it the same amplitudes?
They look roughly the same. That's an acceleration where I think nonlinear just edges out.
Okay. So here we see something different, right? This blue we have more acceleration. Is that right? Oh no, I wrote the opposite, is less than. So in the curve, amplitude of our nonlinear solution is less than that linear. Why is that happening?
I think its rate of change is just different. It's bigger.
Okay.
The more you derivative it, the more it's going to show.
Okay. So something to do with like the fact that we're integrating, or yeah.
Just looking at the velocity graph, it gets up to the peak at a tiny bit faster, so that means its acceleration.
Oh, looking at peak velocities.
Just like how the velocity changes over time, like from 3 to 4, it gets up to the maximum value.
Yeah. So like this slope, at least like so you think like this slope versus this slope are different, like the red and the blue slope, average slope?
Yeah.
Okay. And what is G over L? .3. What is max acceleration for nonlinear, for any angle, for any starting angle? What's the most acceleration that we could have? At 90? And how much would that be? 8.3, yeah. I mean, it could be positive or negative, but somehow. 8.3, like we're fixed. That's as big as it gets. What about for linear? What's max acceleration we can have? Yeah, energy is a good one to look at. What is max? It's no limit, right? The bigger the angle, the more acceleration we have. So as angle, so we can make the angle as big as we want. We can make it a full 360, and it'll swing back around 360 degrees, at least for a linear solution, because we said it's a linear spring. It's just the more you stretch it, the more it comes back. That's fine for small angles, but as you get bigger angles, you get weirder things happening. Like, all right, last example. What if our initial angle is 180 degrees? What happens? So it's upside down. Will it move? Well, according to linear, I'm just saying like theta is, it's always, acceleration's always proportional to theta. It's just gonna move faster because we have 180 degrees, big swing. Numerical looks weird, like as if it's stable and then something fell. But it's also very strange, like y-axis. 1 times 10 to the negative 10 plus 1.8. So really it's 180 degrees plus or minus 10 to the negative 10. And sure enough, we see like it'll just stay there because there's nothing to like force it to go over. There's no acceleration because sine of 180 is 0. So I'm showing this as like different ways of kind of getting at where are differences. So you can either talk about differences of like, for different initial angles, there are different physics happening, like different things. Linear and nonlinear become more spread apart or more converged. So you can talk about that. You can also look at like just this graph. Why is this one there? I'm surprised. Shouldn't acceleration be 0? Oh, I gotta rerun this one. There we go. So you can look at like this output of the graph of like, okay, this is for this initial condition and this length. This is where I'm seeing differences in either amplitude or time period or both. So all those are ways of tackling like that first part. And then when it's time to quantify that error, that should be a real number, like not not a hypothetical, like you could measure this. It's what is the difference? How, like, amplitude is different. Is it within whatever 5% or 5/10 of a degree? Where are we seeing that difference? All right, I'm gonna stop talking and check in with people, because the next step is, what other calculations could we look at? So one suggestion came up of energy, like looking at the energy in this system. But I want to know what else you think about for comparing linear and nonlinear kind of solutions. Oh, take another derivative. Yeah, that was called the jerk system. Yeah. Yeah. Yeah, yeah, that would be it. Oh, like the initial force. So, usually the way, like an initial force is sort of modeled is like if you have an initial speed, because that has momentum, mass times velocity, you can say that there is like an impulse at time zero, so something that's set off in motion. So that's usually how, at least like dynamic systems like this, have your equation of motion is unchanging, and then maybe the initial relation is like some initial hit onto the system kind of starts d0 is next.
Just trying to think about the question.
Okay.
Writing down the sentences and then
Okay. Any ideas for like other comparisons between the two? Okay.
maybe like you said energies.
Okay. So we're not trying to like look at they're both describing motion. So what are, like, if we have a swinging pendulum, one of the things we talk about is the time period. What's that? Control layer. How much speed do you have? What else would be there? Or distance traveled. Yeah. Yeah, what is the right, we got stuck on, at least like we're in the wagon rut of like energy. Energy is the only other thing that we care about for this system. It's not true. Energy's a great thing to compare here, and it has there's some weird like interesting things that come out of it. But if you have like a system, like a pendulum kind of system, it could be like a crane that's like loading things, and as you're moving the crane, it's the payload is swinging around. What do we care about as engineers? Like, we do care a little bit about like the frequency that it is moving at, the amplitude, so like how much motion we have. What else would we care about? Momentum, yeah. So we could look at like what's momentum here. So we could take right now we have theta dot, so we could change that into like mass times L times theta dot. Like what's the magnitude of like changing momentum there? Yeah. All right, so we said energy. What would the energy be? How much energy does a swinging pendulum have? Okay. Potential, so gravitational, what does gravitational potential look like? What is that? M times G times H, is that right? MGH? Okay. And then there was, what was the other part? 1/2 mv squared. So what's our height of a, I have theta calculated for all points in time. What is H? Okay, so it's got to be from here to there? Okay, what is that height? Some kind of L cosine theta?
Okay, it should be the initial length minus, I think, L cosine theta. It will be different.
Kind of like this, like an L, and then minus L cosine theta. Okay, yeah, I'm down with that. So MGL 1 minus cosine theta. And then how fast are we moving? What's V? Or V, really we need like V squared, right? L squared theta dot squared, something like that. L times theta dot is how fast we're going. L squared theta dot squared. Okay. What about supporting this? What are the forces that the pendulum is exerting on our, so right now it's just like bolted into an imaginary like surface of the earth, like just like as if our crank was right into the surface, how much force is being applied there? Do we know? Because that might be a quantity of interest, right? At least if you're building something and someone says, you know, like, okay, it's going to move like this, it's got this acceleration, it's got that momentum, all this energy. Like, all right, well, how big of a bolt do you need to hold it? And you're like, 22 joules? 42 joules? It's like, we don't build bolts in joules. How strong does it need to be? How do we know? Yeah.
It just be like the force of tension.
Yeah. So we have, like, our equation of motion was that this is G over L sine theta, but we also have like mgl cosine theta minus t equals ml theta dot squared. So we have an equation for tension too. And that might be an important distinction of like, is it okay to use a linear versus a nonlinear if the tension value is very different? So we got like a 1, a 2, 3. How much time? Yeah, we got time. What do we want to do? Look at tension or energy or momentum, angular momentum. We didn't even get into that. What do we want to get into? I'll do one example and then leave, and we can call it a day. One, 2, or 3. Who says 1? Momentum of like plotting, okay. Or energy, look at like what are the energy, or tension, like how much tension do we have? Few, okay. Let's look at tension, see what the difference is. All right, so coming back up here, let me change this back to, so 30 degrees, that was kind of, well, let's go 30. I'll put it back to 30 degrees because it was close, but definitely different. If it's 10, then we didn't really see any difference. So here, let's test my theory that 30 degrees is a small angle. So now I've got these graphs. They're the same, but a little different. So I'm going to come up here. I'm just going to grab all of this to start because it has all the variables that I'm going to care about. So I don't need like subplots, and I only need one y label. So the main thing is that it's mgl cosine theta plus that ml theta dot squared. That's my like, and we can't see that, can we? Scrolling up. So,
How are all the terms positive difference, right?
oh, I miswrote it. This should be, because AR is R double dot minus R theta dot squared. So when I plug it in there, it should be a negative M. Yeah, so it does, the T becomes positive, that one becomes positive. Good to check the math. So I'm just gonna write it out to start. It would help. And my d theta is going to be that, the linear solution. SOL y is my nonlinear solution. So I'm going to take this whole thing, let's just copy this. Y0 is my first output from that SOL. That's all my angles. And then this one, I'll call it SOL Y1 and square that one. And now this is no longer lin, it's that nonlinear. Bless you. Oh, it would help if I had mass defined. It might be defined somewhere in there, but let's call it 1 kilogram. Or you could say that it's like tension per mass. Like the bigger the mass, the more tension we have. How do the answers look? It's okay, right? Seems to be about right. So linear, nonlinear, not a big difference for 30 degrees. So maybe that makes sense. Like, yeah, we can do either one as long as it's less than 30 degrees. So let me try 60. Just increase that initial angle. At 60 degrees, we see a bigger difference between our two solutions. So I would imagine we'll see more of a difference in tension. So let's say the angle was 60 degrees and we were using a linear solution to set, like, okay, this is how strong our cable needs to be. Is that okay? Yeah. It accounts for more load. Is that what we're seeing here? Is that we're getting a bigger load with a linear solution? It seems like it, right? Like so it's okay. So even in this case where maybe our time period is a little off, if all we care about is how strong this rope needs to be, linear makes sense because it's automatic, like, factor of safety. Like, it gives us a little bit of, like, the actual value was somewhere in here, like 22. Our linear said it's going to be 24. So it's like close, but a little higher, and that's okay. Unless we're trying to optimize design, then we're just like adding extra steel for no reason, or whatever the cable's made out of. Cool. But this is that last step of just taking some other kind of analysis, like grab the variables that we've already defined and make your own plot. Like, what are you trying to do here? It can be anything. You can choose like any other parameter, just something other than like theta dot, theta double dot. Another idea came up of the path. Like, what does it look like as it's moving around? What are the X and Y locations? And that would be cool too. It should be a smiley face, right? Like a little circular arc. But for, like, if you look at 180 degrees, it should be a dot because it should stay in one place, and the other one's going to be a full circle as it swings all the way around. Cool. All right, have a couple minutes left. I'll just check in, see what other questions there might be, and then we'll call it a day. Any big questions overall? No? Okay. Main things that came up as I was walking around was like, do you need to do any Python coding? Like, are you allowed to use the stuff that's there? Like, you use everything that's written here. If you want to change the graphs or like change the formatting or anything about them, you're welcome to, but you don't have to. You can just use exactly this input output that we have so far. And then the last part is where you're actually making your own plot, like try to get some kind of physics and get a little more information out of it. Yeah? Cool.
Yeah, and it should, I mean, for the most part, it comes down to like if you think about it, when you're on a swing, the acceleration keeps like dropping. There's less acceleration as you go up. Yeah. But if they're linear, it's just super always big. Yeah.
Yeah, so it makes sense that it's like maybe a stroke analysis on a thing like this 10.
Yep. Yeah, yeah. Yeah. All right, great to see you. that one's like, that one's just calling the noun. There's a variable called SL, and it has a bunch of like stuff inside for it. How many functions are there? Yeah, there's like SOL dot. Well, theta, whether it's theta or like SOL, it's kind of same amount. You can have it be the same amount of data, but it's not necessarily the number of data points is changing. There is a relationship between like time steps, how big your time steps are, and how accurate your nominal things. But that one doesn't apply for like sine or cosine. Those are function, whatever you value them at. That's what they are. Yeah.
You mentioned switching this to criteria to check thing. I'm not sure if this is supposed to be like a you or and I guess
What did you say was your x value?
oh wait, isn't it